Now that we have seen the impact of NLP, let us move to the core components. These components are the building blocks of most NLP workflows. If you understand them, the later examples will be much easier to follow. The first component is tokenization. Tokenization is the process of breaking text into smaller units called tokens. When we talk about the cost of using an API, we usually do not talk about words, we talk about tokens. Tokens often correspond roughly to words, but not exactly. A token can be a word, part of a word, punctuation, or sometimes a larger unit depending on the tokenizer. Tokenization converts unstructured text into a form that a model can process. For example, if the sentence is NLP is fun, word tokenization might produce the tokens NLP is fun, and the exclamation mark is its own token because punctuation may carry meaning. There is also sentence tokenization. If the text is NLP is fun, let's learn. Sentence tokenization separates it into two sentences, NLP is fun and let's learn. This is useful when we want to process a document sentence by sentence rather than word by word. Fortunately, we do not do tokenization manually. Python libraries such as NLTK and spaCy provide reliable tokenizers, and we will use them in practical examples. The second component is lemmatization. Lemmatization reduces a word to its base form, called its lemma. The purpose is to normalize related forms of the same word so they can be treated consistently. For example, running becomes run. The word better becomes good. This is different from simply cutting off endings. A proper lemmatizer tries to return a meaningful base form. Again, Python libraries help us. In NLTK, one common tool is the WordNet lemmatizer. We will use it later to reduce variation in text data before analysis. The third component is named entity recognition, or NER. NER identifies and classifies entities in text into categories such as people, locations, dates, organizations, and sometimes products, money amounts, or events. This is one of the most important ways to turn unstructured text into structured information. For example, consider the sentence, "A researcher from the Free University of Bozen-Bolzano presented a study in Bolzano in 2026. A named entity recognition model should identify Free University of Bozen-Bolzano as an organization, Bolzano as a location, and 2026 as a date. Once those entities are extracted, they can be stored, searched, counted, compared, or used in a larger knowledge graph. Libraries such as spaCy and Hugging Face transformers provide models for NER. Many of these work out of the box for common categories, although accuracy always depends on the domain, language, and quality of the text. These three components already show the character of NLP work. Tokenization decides what the basic units are. Lemmatization reduces unnecessary variation among those units. Named entity recognition identifies units that refer to real-world objects or concepts. Later, when we classify sentiment or retrieve documents, we are still building on these earlier decisions about how language should be represented. There is no single pre-processing recipe that works for every task. For a word frequency analysis, removing stop words and lemmatizing may be useful. For a generative model, we may preserve more of the original wording. The important skill is to understand what each step changes in the text. The next component is stop word removal. Stop words are common words that often add little analytical value in a particular task. In English, examples include the, and, is, there, and that. These words are grammatically useful, but they may not help much when we are trying to identify the main themes in a dataset. The reason to remove stop words is to reduce noise. If we are analyzing thousands of reviews, we usually do not want the most frequent words to be the and. We want the terms that carry more domain-specific information. For example, the sentence, "The weather is nice today," might become "weather nice today" after stop word removal. That shortened version is not elegant English, but it preserves the key content for many text analysis tasks. NLTK provides a stop words list that we can use directly. As with tokenization and lemmatization, you do not need to memorize every import or every function name. The practical skill is knowing that these tools exist, knowing when to apply them, and being able to reuse a reliable preprocessing pattern in your own code. Putting these components together, a typical NLP preprocessing workflow looks like this. We begin with raw, unstructured text. Then we tokenize it. Next, we remove stop words. Then we reduce words to their base forms through lemmatization. If the task requires it, we can also apply named entity recognition to extract structured information such as names, locations, dates, and organizations. Only after these steps do we usually begin model training or downstream analysis. We do not normally feed messy raw text directly into a classical machine learning pipeline. Pre-processing is the work that turns language into something more consistent and useful. This is also where much of the real labor happens. In applied NLP, pre-processing can easily take the majority of the project time. Sometimes 80 or 90% of the effort is spent cleaning, normalizing, checking, and restructuring the data before the model is ever trained. That is not meant to discourage you. It is meant to set realistic expectations. The quality of the model is often limited by the quality of the text pipeline that comes before it. With those building blocks in mind, we can now move from definitions to demonstrations. We will look at a few real-world style examples of NLP in action. The first and most visible example today is the chatbot. For this course, I built a small question-answering assistant. It is not the public ChatGPT interface. It is a simple application designed to show what happens when we connect a front-end to language model APIs. The important point is that the system is not large or mysterious. A basic prototype can be built with a small amount of code once you understand the structure, a prompt, a model call, a conversation history, and a response. As you watch the example, focus less on the visual interface and more on the data flow. The user writes a question. The application packages that question with instructions and, if needed, previous messages. The selected model produces a response. The application displays the response and stores enough context to continue the conversation. That loop is the foundation for many chatbot systems. The chatbot demonstration uses several APIs and several models. In an updated version, the user might choose a current hosted GPT model, a DeepSeek family model, or a Llama family model. The specific model names change over time, but the design point remains the same. The interface can remain stable while the underlying model changes. In the application, the user selects a model from a drop-down menu and then asks a question. For example, we might ask a question about the Free University of Bozen-Bolzano. The model returns an answer. Then we can switch models and ask a follow-up question such as, what is NLP? The interesting part is that the second model can still use the previous conversation context if we pass that context into the prompt. This illustrates a central design idea in chatbot systems. The model itself does not automatically remember everything in a human sense. The application sends relevant conversation history along with the new user input. That history gives the model context for the next response. So when the model appears to remember that we were talking about the university, that behavior is produced by the way the application passes previous messages into the next model call. Some reasoning-oriented models can also produce intermediate reasoning traces or explanations, depending on the interface and configuration. In a teaching setting, that can be useful because it shows how the model interprets the relationship between the previous question and the current one. In production systems, however, we would think carefully about what reasoning or explanation should be shown to users. The code behind this kind of prototype is not very large. Much of what you see in the interface is front-end code, buttons, a drop-down menu, predefined prompt examples, and a chat layout. The core model interaction is usually much smaller. It consists of a structured prompt, the conversation history, the selected model name, and the API call that sends the request and receives the response. In this example, the front end was built with Chainlit, which is a framework for quickly creating conversational AI interfaces. Underneath the interface, the application chooses between several model providers or model families based on the user's selection. You could add other models in the same pattern. This is intentionally a basic chatbot, not a full RAG system. A basic chatbot responds from the model's existing knowledge and the context we provide in the prompt. A RAG system adds another step. It retrieves relevant external documents or data first, then passes that retrieved context to the model. We will build toward that later because it is one of the most important practical architectures for business applications. The takeaway is that a useful chatbot prototype is not out of reach. Once the interface is in place, the central logic can be described in a compact function. Collect the current user message, include the conversation history, select the model, call the API, and display the answer. From there, we can improve reliability, add retrieval, improve prompts, add evaluation, and handle privacy and deployment concerns. This also gives us a clean way to compare models. If the same user question, same prompt, and same conversation history are sent to different models, we can inspect how their answers differ. One model may be faster, another cheaper, another better at reasoning, and another easier to run locally. Choosing a model is therefore an engineering decision, not only a question of which model is most famous. From that basic chatbot, there are several natural extensions. One is to connect the model to external materials, such as course documents, company policies, or a knowledge base. Another is to connect the system to web search or another retrieval tool when current information is required. Standard language models are trained up to a certain point in time, so they do not automatically know about events or documents that appeared afterward. Retrieval and search are ways to address that limitation. The basic architecture remains the starting point. A user interface, a prompt, a selected model, and a response. Once that is working, we can add retrieval, web search, document upload, evaluation, and guardrails. In this course, we will build from simple examples toward those more complete systems. Now let us return to the slides and move to another common NLP application, sentiment analysis. In sentiment analysis, we estimate the emotional or evaluative tone of a text or conversation. The output might be simple, such as positive, negative, or neutral. It can also be more nuanced, mixed sentiment, frustration, urgency, enthusiasm, uncertainty, or customer dissatisfaction. There are specialized models built specifically for sentiment analysis. There are also large general-purpose models, including current hosted GPT models and open-weight LLMs, that can perform sentiment analysis directly from a prompt. Because these models are trained on broad language data, they often handle this task well without additional training, especially for short examples. The next demonstration is a small sentiment analysis chatbot. Much of the code is again interface code. The important part is the logic that tracks the conversation and asks the model to classify the sentiment of the current exchange. The app can count messages, display the current sentiment label, and provide a short explanation of why the sentiment was classified that way. When building local demonstrations, small technical issues can happen, such as a port already being used by another process. In a recorded version, the instruction is simply this: start the local app, switch to an available port if necessary, and then open the app in the browser. What matters conceptually is not the port number. What matters is that the model is analyzing the conversation as text and returning a sentiment classification with an explanation.